What if everything we thought we knew about the universe was just a small fraction of the truth? Every twinkling star you've ever seen, every swirling galaxy, every glowing nebula, all of it combined makes up less than 15% of what truly exists. The rest? It's dark, unseen. Yet its invisible pull shapes the motion of galaxies, the bending of light, and the very structure of the cosmos. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast congregation of galaxies millions of light years away. But something didn't make sense. These galaxies were moving so fast that, by all logic, they should have drifted apart long ago. The visible matter, stars, gas, dust, simply wasn't enough to keep them bound together. Something invisible, something massive, was holding them in place. Zwicky called it dunkle materie, dark matter, a mysterious glue of the universe that no telescope could see. For decades, Zwicky's claim lingered in the shadows, a strange idea with no proof. Then, in the 1970s, Vera Rubin, an astronomer with a quiet determination, began measuring how stars moved around spiral galaxies. What she found changed everything. The stars at the edges, far from the galactic core, were spinning just as fast as those near the center. According to Newton's laws, they should have been flung into the emptiness of space. But they weren't. Something unseen was providing the extra gravity to hold them together. It was the invisible fingerprint of dark matter, the hidden framework keeping galaxies intact. This mysterious substance acts like an unseen hand, guiding galaxies, bending light, shaping the cosmic landscape. When astronomers look deep into space, they see distant galaxies whose light bends and stretches around invisible structures, a phenomenon called gravitational lensing. It's as if vast, transparent halos of matter are warping the very fabric of space itself. And when scientists mapped the faint afterglow of the Big Bang, the cosmic microwave background, they noticed tiny ripples in temperature across the sky. Those subtle patterns were not random. They revealed a hidden architecture, a cosmic skeleton made of dark matter. It's this web that dictated where galaxies would later form, weaving the large-scale structure of the universe. Yet, despite all this evidence, we still don't know what dark matter actually is. It doesn't emit light. It doesn't reflect, absorb, or interact with ordinary matter, except through gravity. Some scientists think it could be made of yet undiscovered particles. Others believe it might be something even stranger, a sign that our understanding of gravity itself is incomplete. But one thing is certain, without it, the universe as we know it could not exist. Galaxies would never have formed. Stars might never have ignited. And we, the observers trying to understand it all, would never have come to be. Before we ever knew what it was, we could already see its shadow written in gravity itself. The hidden universe of dark matter. Everywhere we look in the universe, gravity is pulling on something we can't see. It's there in the movement of galaxies, in the bending of light, in the structure of the cosmos itself. We call it dark matter, but if it's all around us, why can't we find it? Why can't we see it? The answer lies not in what it is, but in what it's not. Everything you've ever touched, seen, or imagined, stars, planets, clouds, oceans, even you, is made of the same kind of stuff, baryonic matter. That means it's built from protons, neutrons, and electrons. These tiny particles have a special property. They interact with light. They can reflect it, absorb it, or emit it. That's why your eyes can see the world around you and why telescopes can peer across the cosmos. Light tells us what the universe is made of, but dark matter? It doesn't play by those rules. Dark matter doesn't interact with light at all. It doesn't reflect it. It doesn't emit it. It doesn't even absorb it. In fact, light passes straight through dark matter as if it weren't even there. That's why no telescope, no matter how powerful, can ever take a picture of it. It's like trying to photograph the wind. You can only see what it moves, never the wind itself. When scientists first discovered evidence of dark matter, some thought it might just be ordinary matter that doesn't shine. Perhaps it was massive compact halo objects, or machos, like black holes, or faint, cold gas clouds, or even lonely planets drifting through the void. But as astronomers did the math, the puzzle grew deeper. There simply weren't enough of these dark objects to explain the immense gravitational pull observed in galaxies. The observed rotation of stars at the edges of galaxies was much faster than visible matter alone could account for, strongly suggesting additional unseen mass. Gravitational lensing, where massive objects bend light, also showed greater bending than visible matter could explain, further pointing to dark matter. Whatever this mysterious matter was, it wasn't made of protons, neutrons, or electrons. It had to be something completely new, non-baryonic matter, a kind of particle we've never seen, but that makes up most of the universe. Scientists theorize it could be weakly interacting massive particles, which are massive and interact weakly. Other candidates include extremely light particles called axions, or even primordial black holes formed in the early universe. Right now, as you watch this, trillions of dark matter particles are streaming through you. Every second, billions pass through your body, through the earth, through everything you know. And yet, they leave no mark. They don't collide with atoms. They don't heat us. They don't glow. They simply pass through, silent, invisible, and eternal. It's a strange thought, isn't it? That most of the universe is made of something that doesn't care about us, something we can't touch, see, or feel, yet it's everywhere. Dark matter provides the gravitational scaffolding for galaxy formation, pulling ordinary matter together to allow galaxies to form and grow. It also influences the large-scale structure of the universe, shaping the cosmic web of galaxies and voids we observe today. Scientists are actively searching for dark matter through direct detection experiments deep underground, like Super CDMS PICO and LZ, hoping to catch a rare interaction. Indirect detection experiments, such as the Fermi Gamma Ray Space Telescope and IceCube Neutrino Observatory, search for products of dark matter annihilation, like gamma rays and neutrinos. Even particle accelerators like the Large Hadron Collider are trying to create dark matter particles in controlled collisions. It's important to distinguish dark matter from dark energy. Dark matter is a form of matter that interacts gravitationally, but not electromagnetically. Dark energy, on the other hand, is a mysterious force causing the expansion of the universe to accelerate. Dark matter makes up about 27% of the universe, while dark energy makes up about 68%. It's as if the universe is built on a hidden foundation, a framework we can't see, but that holds everything together. Dark matter doesn't glow, doesn't speak, doesn't reveal itself easily, but its presence is undeniable, written not in light, but in the quiet pull of gravity itself. This hidden foundation continues to shape our cosmos, a silent architect of the universe. Knowing that something exists and proving it are two very different things. For decades, scientists have watched dark matter's invisible hand-shaped galaxies bend light and sculpt the universe. But seeing it, detecting it, that's the hard part. And so began one of the greatest hunts in modern science, the search for dark matter. Far below the surface of the Earth, under mountains in Italy, Japan, and South Dakota lie enormous underground laboratories. These silent cathedrals of science are buried beneath kilometers of rock, shielded from cosmic rays and background radiation. Why so deep? Because what they're trying to detect is almost unimaginably subtle. Inside these chambers sit vast tanks filled with ultra-pure liquid xenon or argon. Every atom in those tanks waits, patiently. So far, those flashes have been incredibly rare. Most nights, the detectors stay silent. Each day that passes refines the search. Because the truth, hidden deep in that stillness, could be waiting in the next collision, the next flash, the next heartbeat of data. Meanwhile, in Switzerland, beneath the French border, another kind of hunt is taking place. At CERN's Large Hadron Collider, protons are smashed together at nearly the speed of light. In the chaos of those collisions, scientists hope to create dark matter itself to summon, for a brief instant, the invisible particles that have eluded us since the beginning of time. But the hunt doesn't stop underground or inside particle accelerators. Astronomers are searching the heavens for clues. By studying how light from distant galaxies bends around invisible masses, a phenomenon known as gravitational lensing, they can map the hidden distribution of dark matter across the universe. And what they've found is extraordinary, a vast, web-like structure connecting galaxies across billions of light years. A cosmic skeleton woven from dark matter. From the deepest tunnels on Earth to the farthest corners of space, humanity is chasing a shadow, searching for the unseen foundation of everything we know. Each experiment, each silent detector, each cosmic map brings us one step closer to answering the most profound question of all. What is the universe really made of? Dark matter is not just an invisible mystery. It's the fundamental scaffolding of existence, the silent architect that meticulously built the universe we inhabit today. This enigmatic substance, though unseen, dictates the very fabric of cosmic structure. Without dark matter, there would be no galaxies, no stars, and no cosmic order whatsoever. From the very earliest moments of the universe, it was dark matter that provided the essential framework, giving structure to the initial chaos and allowing matter to coalesce. In the immediate aftermath of the Big Bang, the universe was a nearly uniform ocean of elementary particles. It was incredibly hot, extraordinarily dense, and almost perfectly smooth, a primordial soup of energy and matter. However, it was not perfectly smooth. Tiny, quantum fluctuations in density existed across this cosmic sea. These were small, almost imperceptible ripples, but they held the key to the universe's future evolution. Dark matter's gravity began to exert its influence on these minute ripples, subtly tugging on them. It pulled ordinary matter into invisible gravitational wells, creating denser regions that would eventually become the foundational building blocks for all large-scale structures in the cosmos. From these invisible seeds, these initial concentrations of matter, the first stars ignited, illuminating the dark universe. Subsequently, these stars aggregated into the first galaxies, which then clustered together to form vast cosmic structures stretching across immense distances in space. Dark matter didn't merely exist within the universe. It actively shaped the universe itself. It was the primary force sculpting its grand, intricate architecture, guiding the formation and distribution of all visible matter. Over billions of years, the persistent gravitational pull of dark matter sculpted the cosmos into a grand, interconnected network known as the cosmic web. This immense structure, composed of filaments and voids, stretches across billions of light years, defining the large-scale organization of the universe. Each filament, each delicate thread of that cosmic web, acts like a gravitational highway. These highways funnel gas and dust into denser nodes, which are the cosmic nurseries where new galaxies are continuously born and thrive. If, hypothetically, you could somehow remove dark matter from the universe, this vast and intricate architecture would instantly destabilize. The delicate balance holding everything together would be lost, leading to an immediate and catastrophic collapse. Without dark matter's cohesive force, galaxies would tear apart, their stars scattering into the void. Clusters of galaxies would dissolve, and individual stars would drift aimlessly into the emptiness, losing all their cohesive structure and form. Dark matter is, in essence, the cosmic glue, the invisible framework that holds everything together. It maintains the structural integrity of the universe, ensuring that galaxies and clusters remain bound and organized. But while dark matter tirelessly binds the universe together, another equally mysterious force is actively trying to pull it apart. This opposing force, known as dark energy, represents a profound cosmic enigma. Dark energy is a strange, pervasive, and repulsive energy that appears to fill all of space. Its primary effect is to push space itself to expand at an ever-increasing rate, driving galaxies further and further apart. Currently, the expansion of the universe is not just happening, it is accelerating. Scientists and cosmologists worldwide are still striving to fully understand the fundamental nature and origin of this mysterious phenomenon, which continues to defy complete explanation. We understand that dark matter exerts a gravitational pull, drawing things inward and fostering structure. Conversely, dark energy exerts a repulsive force, pushing everything outward and accelerating the universe's expansion. Together, these two invisible giants are locked in a perpetual cosmic tug-of-war, a silent yet monumental battle. This ongoing struggle is profoundly shaping the past, present, and ultimately, the future destiny of the entire universe. So what happens next in this cosmic drama? If the gravitational pull of dark matter proves to be strong enough, it could eventually slow down the universe's relentless expansion, potentially altering its ultimate trajectory. It's even conceivable that dark matter's gravity could cause the expansion to reverse entirely, leading to a dramatic event known as the Big Crunch. In this scenario, everything would collapse back into a single, incredibly dense point, much like the inverse of the Big Bang. However, if dark energy continues to dominate and its repulsive force prevails, the universe will continue to expand indefinitely, leading to a vastly different and perhaps more desolate fate for all cosmic structures. In this scenario, galaxies will drift so incredibly far apart that their light will eventually become undetectable to one another. Each galaxy will become an isolated island in a vast, ever-expanding emptiness, losing all cosmic connection. Eventually, all stars will burn out, exhausting their nuclear fuel and fading into darkness. The cosmos will then slowly descend into a state of uniform, cold, and silent darkness, a chilling future known as the Big Freeze or heat death. Between these two powerful, invisible forces, one relentlessly pulling together, the other ceaselessly pushing apart, lies the ultimate, uncertain fate of everything that exists. The balance between them will determine the universe's final chapter. In the end, the profound destiny of the cosmos depends not on what we can readily observe and comprehend, but rather on the mysterious, unseen forces that continue to elude our complete understanding. As of November 2025, dark matter research stands at a thrilling crossroads. Decades of searching, countless experiments, and yet the mystery deepens. For the first time, some physicists believe that dark matter might not be just one kind of particle, but an entire dark sector, a hidden mirror world with its own particles, its own forces, and maybe even a kind of dark light we simply can't perceive. Around the world, new eyes are opening to the cosmos. At the Vera Rubin Observatory, powerful telescopes will soon capture vast panoramic views of the sky, mapping how galaxies move, twist, and cluster under the invisible pull of dark matter. Deep underground, experiments like xenon antiweight in total silence, giant detectors filled with ultra-pure liquid xenon, searching for a single spark from a passing dark matter particle. Every year, our instruments grow more precise, our understanding sharper, our curiosity stronger. Each data point, each faint signal, pushes us closer to an answer that could redefine physics itself. But even as we build better machines and collect more evidence, dark matter challenges something deeper, our very perception of reality. What does it mean that most of the universe, 85% of it, is invisible to our senses? That the world we see, feel, and measure is just a small fraction of what truly exists? Maybe dark matter isn't just a physical mystery, but a philosophical one. Perhaps it's a reminder of human limitation, that no matter how advanced our technology becomes, there will always be more waiting beyond the horizon of our understanding. Or maybe it's an invitation to keep questioning, to keep exploring, to never stop wondering what lies beyond the visible. Because every time we push deeper into the darkness, we don't just learn more about the universe, we learn more about ourselves. The search for dark matter isn't just about science. It's about connection between what's known and unknown, visible and invisible, seen and felt. Because the deeper we look into the darkness, the more light we find within ourselves, the light of curiosity, of imagination, of discovery. The cosmos is whispering secrets across billions of years, and dark matter, quiet, invisible, patient, may be its most profound voice. If you enjoyed this journey beyond the visible, make sure to like, share, and subscribe.